Alright, hello everyone, this is the 10th lecture of vibrations and waves, and today we will be discussing Fourier analysis. We start with a string fixed from both sides, and we take this string up some point at t equals 0, and we leave it. Now we know that as we make that we pull the string up and leave it, we know that it should start oscillating at a superposition of the normal modes. And that brings us to two questions. The first one, how can we describe the string when we bring it up at that point? So at time t equals 0, how can we describe the string? And the second question is, what are these normal modes and what are the amplitudes of these normal modes? Okay, so we have y of x and t. This is the y direction. In general would be summation n from 1 to infinity of some amplitude bn sine k n x cosine omega nt. So this is the general form where kn is n pi over l. L is the length of the string, and omega n equals v times kn. Now at time t equals 0, we have y of x0 equals to b1 sine k1 x plus b2 sine k2 x plus b3 and so on. So the objective now, down here, objective is to find what values of n that we sum over here for the modes are necessary to construct a pulse that we make at this time t equals 0, and what are the amplitudes? What are bn? So these are the two things that we want to find. How can we construct this string at this time t equals 0? And what would be the amplitudes of the modes that play a role in the in this physical situation? Okay. So let's start with a general approach, and then we go back to this question. So general approach, I'll write down here, any periodic single valued function with period 2 pi can be represented by a Fourier series. Now note that we're moving to radians now, it's no longer in meters. So I'm going to give you the recipe in for the general case in radians, and when we come back to this specific problem, we're gonna translate that back into meters. All right, so we have a function f of x, and that function I can write it as some constant. Now I could write c for that constant, but I'm going to write a0 over 2. You're going to see why later on. Plus a summation over, we take m from 1 to infinity, some amplitudes am cosine mx plus n m from 1 to infinity of b m sine mx. Now, any function, any periodic single values function that you can think about, Fourier says that you can represent it in the following format. It can be a constant plus the superposition of these cosines and sines. Okay, so our task now is to find the values for a and b. So find the task, find the values a and b. So all am and a0 and bm. To do that, we make a few steps. First step, we take this function so we take this function in the first step and we integrate both sides from minus pi to pi dx. So integrate this side and we integrate the right side. Now look what you would have. So on the left side I'm going to have a integral from minus pi to pi fx equals to, on the right side we're going to have integral over this term, the second term and the third term. But the integration over one period for any cosine mx here or a sine mx is 0, right? So the only term that survives on the right side would be a0 over 2. So that would be minus pi to pi a0 over 2 dx. And that gives us that a0, if you make the integration, you end up with pi a0 here, which means that a0 is, write it down here, is 1 over pi integral of minus pi to pi of fx dx. And we know this function fx. We want to know the values of a and b. So we found a0. And I'm going to write it here. So a0 is 1 over pi integral from minus pi to pi of the function fx dx. The next step is to make a similar integration, but you multiply with a cosine nx dx. Now if we do that, notice now you have a cosine here. This is just a constant. So you'd have a cosine here, cosine nx. And when you make the integration over one period, that gives you a 0. So the first term gives a 0. The third term is a cosine times a sine, and it would always give you a 0 for any values of a integer n and m. It will always give you a 0, the product of cosine times sine. Also, the values here with cosine mx times cosine nx, when you make the integration, that would also give you a 0 for all n and m that are not equal. Okay, so if n and m are different, cosine mx times cosine nx, that would give you a 0 as well. So the only terms that won't be 0 is the cosine squared. So when m equals to n. So when we do the second step, on the left side we would have minus pi to pi integration over f dx, and on the right side the only the only term that survives would be am cosine squared mx dx. Okay, and you know how to do this. The cosine squared will give you 1/2, and you go over a period from minus pi to pi. So you have 2 pi at the end of the day. You would get, you can write it here. So you get am equals 1 over pi integral from minus pi to pi fx times something missing here. We say we multiply by cosine mx or nx. So this would be n and m are equal here, so it doesn't matter, just for the consistency to have everything with n. Alright, please correct this. So the result would be that we found a n now, and that is 1 over pi integral from minus pi to pi fx times cosine nx dx. So we found a n. Write am, doesn't matter. Am is 1 over pi from minus pi to pi fx times cosine mx dx. Similarly, now we go to step number 3. Now we multiply the right and left sides here by a sine n of x, and similar to what we had before, the integration, let me write this down first. So step number 3, we integrate from minus pi to pi both sides, and we multiply by a cosine sine now, sine nx. So when we multiply the a0 over 2, we have a sine there for the same reason as before. We integrate over one period, that gives us 0. Sine times a cosine is always 0 for any n and m. Sine times a sine also gives a 0 when n is not equal to m, and the only place where it's not a 0 when n is equal to m. And then in that case we have a sine squared of nx, which gives us a half. So we can write from minus pi to pi fx times sine nx, that's on the left side. And the only thing that survives on the right side would be now bn times sine squared nx dx. And again, this gives a 1/2, and then it goes from minus pi to pi, then this is 2 pi, so in total it would give a 1 over, it would give 1 pi. So now we can write Bn, we found Bn, that would be 1 over pi times fx sine nx dx. I'm gonna write it here as well. I'm gonna make use of this. So now we found also Bn. And Bn is 1 over pi from minus pi to pi fx sine mx dx. So we found the amplitudes for the that we were looking for in the function. Alright, so now given any function fx, we plug it here, we can find the constants, the amplitudes. But we first should be aware that when we do that, we have to go back from the radians, because x here is in radians. We're going to go back to meters, because the problem that I had here, string, this is in meters. So we need to make a little translation now. Yeah, before we do that, I just want to mention that if you note here, we have A0 here, and this A0 here basically gives the average over the function. Okay, and we could have it as a C, as a constant, and then we would get C equals 1 over 2 pi. So it's the same thing. It's just it's more convenient to describe it in this way, because now we can take m here. We can take m from 0, 1, 2, and so on, and 0 would actually give us 1 here, would give us A0, and we don't need that one anymore. So we have only two relations here that we can use for AM and BM. Okay, note that A0 over 2 is the average value of the function over 2 pi period. Now let's go back to the string, and before doing that, let's translate this into meters. So we don't have 0 to 2 pi, but we have a length of the length of the string is L. So we want to construct it now. Let's reconstruct it again. Now let's assume, just to make things simpler, let's assume that this is my string, and I pull it in a way that I make it look like a step, like this. And it's fixed here, and it's fixed here. Now the Fourier analysis is about periodic functions, and there is no periodic function here. So the first thing that we want to do is to create a periodic function, and that's fine. I can I can do something like this. Now we have a periodic function. This has a length L. This is my string, and it goes from 0. So this is 0, and this is L. So the period here is 2L. This would be the period. Now before the period was 2 pi, and now the period is 2L. So for AM, I write 1 over L integral from, it's either you can write from 0 to L or from 0 to 2L, right, over one period. So it would be 0 to 2L, or you can write from minus L to L, it doesn't matter. From, let's say, from 0 to 2L, f of x. Now you need the cosine m pi x over n. Now x is in meters, not in radians. dx. Now we do the same thing for the m. Is 1 over L from 0 to 2L f of x sine m pi x over L dx. We know the amplitude. Let's say the amplitude is small a at time t equals 0. We pull this, we make this shape, and then later on we leave. So first of all, we want to describe this string at time t equals 0. Okay, let's describe y. This is y of x and t. So y x, we come to the time later on. Y of x, which is our f x, is a0 over 2 plus summation over am cosine m pi x over L plus bm sine m pi x L. So this describes the string, and we want to look at the string at time t equals 0. So let's take first a1. a1 looks like this. a1 cosine pi x over n. Let's see if this makes sense to use this term here. A1 would be somewhere here, the amplitude. We don't know the amplitude yet, but it's a cosine function, so it should look something like this. It comes from here, goes there, and it goes like that. But this is not good. Why is it not good? We want to construct this shape at t equals 0. And to construct it, I want my functions to add up here to give this shape. And what we see here is that it adds up here, which looks fine, but on the other hand, it adds up here where it should be a valley and not a mountain. So this is not a good solution. In fact, with analogy, you would conclude that all the terms with the cosine, they won't be useful here. And the reason is that in the case of the cosine, you have a function where f of x equals to f of minus x, right? It's an even function. And what we want here is an odd function. We want something that from the right to the 0 point here to be constructive. And if you look at the left, it should be destructive or constructive in the minus sign. Okay? So here it should be plus, and here it should be a minus. So all the cosines, we can say that they are of no use. So we conclude here that all a of m should be 0. It won't help us in this specific problem. Okay, so let's look at b1. b1 sine pi x over L. That would have a shape like this. And this is exactly what we want. Well, the amplitude could be larger or smaller, depends on the constants. But this is exactly what we want. We want something constructed here, and we wanted making a valley here. So a mountain here and a valley on this side. So B1 looks fine. How about B2? B2 is also an odd function, right? Because it's, the sine is an odd function for the second mode. 2 pi. Okay. And it looks something like this. But this is also not good. Yes, it is going to the negative part here. But if I look on this 1/2 period, I want to have some kind of symmetry. And this is what I have here. It's a symmetric. It's symmetric. But here we don't have that symmetry. We have here plus, and on this side is a minus. Another way to think about it is that, yes, I'm adding here on this side, but in the valley here I'm also adding, and I don't want to add there in order to be able to construct. So the conclusion is that S2 won't be useful for us. And in fact, with analogy, you would expect that all the 2m won't be useful. So all these would have to be 0. So let's write down what we found useful. So Bm there's an amplitude, so I can take it out. So A over L integration from 0 to L. This is for the first half. Okay, this from 0 to L is positive sine m pi x over L dx minus A over L from L to 2L sine m pi x over L dx. And this minus sign here would give me the negative values here. So this is positive, first positive, and the other half is negative. And if you make the integration, that gives a minus here from the cosine, and we would have one L outside, so we have a minus AL, and we have L over m pi cosine m pi x over L from 0 to L. Plus, in a similar way, this is with a minus, now it would be with a plus. I get 1 L over m pi, so I have L over m pi, and we had the L, where was it? Yeah, here. Cosine m pi x over L, between L and 2L. Now it's easy to see when m is odd. Let's take m equals 1. When m is odd, so m equals 1. Step 2, and m is even. When m is odd, this would give you a 1, and then only this part. I'm looking at only this part. 1 and another 1. That will give you a minus. That will give you a minus 1 and another minus 1. So it will give you a minus 2. And this would give you a plus 2. When m is even, you see that this will give you 0, and this will give you 0. Okay, so now we can write, I'll do it here. So now we can write Bn, which is 2a plus 2a, that gives us 4a over m pi, which means now we can write our function y at t equals 0. That is 4a over pi times sine pi x over L plus 1/3 sine 3 pi x over L plus 1/5 sine 5 pi x over L, and so on. So if we look at the string at time t equals 0, let's look at the values of B1 and B3 and B5. B1 would be 4a over pi, and that is about 1.27 times a. B3 would be 4a over 3 pi, that is 0.42a. B5 is 4a over 5 pi, okay, and so on. So if I want to draw it, the first mode would be something like this. That's great. It's already giving me something. Well, it's not quite the rectangle, but it gives me most of the build-up of the rectangle. There's some extra here, and there's something here that needs to be filled in. And here comes B3, for example. So this is B1. And B3 would be something like this. So it adds up here and here. It helps building up this further. And it helps also taking away some of the extra thing here. So already by adding the first mode and the third mode, basically the first two effective modes here, I'm getting quite close to the initial shape. And so on, and you can add more. And oh, this is a wrong one. You see there's no symmetry here. I wasn't very careful of putting this in. Should have a symmetry, something like this. Well, now you get the idea. So this would help building up, and this would help taking a little of the extra ones. What we did so far was at yx equal at y with t equals 0. So I can write y of x and t now. It's 4a over pi times sine pi x over L, but there's a cosine omega 1t, and 1/3 sine 3 pi x over L, again times cosine omega 2t, and so on. And now I can describe the motion. So now I can discuss what happens next. Okay, so we were able to construct the string at time t equals 0, and now we left it, and what is going to happen is that it starts to oscillate with these modes. Now you may think that it would start oscillating like that, but that's not true. The modes would be, each one of the modes would be oscillating as a standing wave. But don't forget that the standing waves themselves are a superposition of traveling waves. If you want to think about it in a different way, maybe it's easier to see. If you have the string, and it's a very, very long string now, and you disturb it here, in a symmetric way, it doesn't matter, okay? And you disturb it here. Now recall when we talked about traveling waves, we just made the disturbance, then we had the propagation of the disturbance. Now in that case we had the propagation given as it propagates from left to right. But now you disturb the system in a very in a symmetric way, so there is no preference on the sides. So what would you expect to happen? So you start with this scenario. This is exactly in the middle with some amplitude, let's say A. What you would expect is now the disturbance would start moving in both directions. So at some moment in time later on, you would find it here and here, and it would be with A over 2, each one of them. So this would be moving to the right, and this would be moving to the left. Let's put it down. Okay, so the disturbance is here. After some time, this would be moving to the right. It would split into two disturbances, and they would move to the one to the right and one to the left. But this is a fixed end, and this is a fixed end. So when they come back, they will, you know already that they would come back as a valley like that. Now I hope you understand also that because it depends on the shape of make the pulse in a string, you can do it like this, and you can do it like this, and you can do it like this. If each one of these would have a different Fourier solution, so each one of these will be different. As a result, they oscillate the natural modes that you're exciting, and the amplitudes are different. Even though it's the same string, it's the same length, it's enough that you start with this at t equals 0, a different shape. You're constructing a different superposition of the modes. So the constants Am and Bm are different, and therefore, and musicians know this, if you have a string, a violin or a guitar, and you would do it at one point, or in the middle, for example, or in the closer to the side, the sound would be different. And the reason now you know the sound is different because you're actually exciting the modes in a different way with different amplitudes. All right, let's look at these videos.
So there's some fancy math I learned at the university called the Fourier series. These are my old notebooks. And check this out. The teacher challenged us to create this graph by doing nothing but adding together curves. And I found where I did it. It's right here. And it took me, it looks like 4 or 5 pages. Yeah, it took a lot of pages. And I ended up with this. I was able to make the graph by adding together a bunch of waves, and to demonstrate that, I created this. I had to get a tripod. Here's my flip book. So it starts with one sine wave, and then we add another one, and you can see the more waves you add together, the closer the function gets to what you're supposed to make. Because you can see, like, that and that look very similar. That's 50 waves added together. So it's cool, and it's one thing to know how to do the Fourier series by hand. It's quite another to understand how it works. And I didn't really have that moment of it clicking in my brain until I saw this awesome blog by a guy named Doha from Turkey. He's a student at Georgia Tech. I want to show you this. This made it click in my mind unlike anything. This transcends language. So let's go check out Doha and let him teach you how a Fourier series works. I'm in Georgia Tech. This is Doha.
Hello.
You have visualized via animation a Fourier series in the most beautiful way I've ever seen in my life. Sine waves are probably the simplest kind of wave, right? The second most simple kind of wave is a square wave, but the difference is you have sharp edges in a square wave. The first thing that Doha did to impress me is he used curvy waves to make sharp-edged square waves. We have to add up different oscillations, yes, or simple harmonic motion here.
Harmonics, yes.
Yeah, and so the first harmonic, n equals 1, gives you this,
yes,
which looks nothing like it.
Nothing interesting, just boring sine wave. And I add one more. It's actually like it. I'm adding one harmonic and other one 1/3 of that harmonic radius.
So you're adding a base. What are we going to call these? Wipers?
Yeah, let's call them wipers.
Okay, so we're going to add a wiper on a wiper. And by doing that, and we graph the function,
and then follow the tip of these wipers,
yeah,
and draw that respect to time.
It's awesome, man.
Yes.
Like this is really, really beautiful and really, really simple.
So I can add more wipers, maybe more harmonics, and I add 15 harmonics. It's something very cool.
Oh wow, it looks like a whip.
Yes.
So you're saying, so basically, here's the upshot. A Fourier series, you can create any function as a function or an addition of multiple simple harmonic motion components, right?
Yes.
All Doha is doing is he's taking these sine waves that we explained earlier and he's stacking one on another sine wave. He's stacking the circles to add together these waves to create a Fourier series. These visualization techniques that Doha developed worked on any version of any function. For example, on a sawtooth wave, you can see at n equals 8 how the Fourier series starts to play out. It looks really cool. How did you do this? Like, what program did you use to visualize this?
I use Mathematica.
Mathematica?
Mathematica, yes.
Really?
Yes.
So, if I give you any function, can you create this? But you had to flip it into video format somehow. How did you do that?
I explored it in like GIF. I created a table of the different times of this animation, and then I just exported those tables into GIF. That's all what I did.
Okay, here's an interesting question. Are people? It's actually GIF. I don't know if you know that. So if I were to give you a function, like if I were to give you a super complicated function, like a really weird curve, you could make a graphic like this?
Probably I can, yes.
So I can challenge you.
Yep.
Let me explain what's happening here. Amongst academics, there's this thing that I just now made up called math swagger. And basically it's when a person's good at math, they like think they can do anything with it. It's not like a prideful thing. I mean, Doha's a very humble person, but you could tell he was very confident in what his abilities with math were. So I can challenge you.
Yep.
Which is why I'm challenging him to draw this with the Fourier series. It is that smarter everyday thing that you see all over the internet. I totally am geeking out right now. I love this. It's a hard image to draw using math. It's got like curves, right? It's got little sharp points and switchbacks. It's self-serving for me. So this is an appropriate challenge for somebody that's demonstrating math swagger. The problem is he actually can do it. He can model this using nothing but circles in the Fourier series, which is completely impressive. Check this out. The first thing that he has to do in order to draw this image is to extract the x and y positions that he would need to make functions for in order to make this thing work. He then needs to create a Fourier series for each one of those functions so that he can add them together. And as you can see, these first few were not winners. I mean, like, no stretch of the imagination could make your brain think this looks like the side profile of a human head. Everything's a bit derpy. But as he starts to refine it and he adds more and more waves to the functions, things start to hone in and it starts to look really good. At about 40 circles in this whole function, things start to look really good and your brain would totally think that you're looking at a drawn image instead of a mathematically drawn function. If you look closer at just one of these arms, you would think that it's chaos, but it's not. It's complete order backed up by a mathematical function. In fact, this is why I love math. It's the language that describes the entire physical world. We can approximate anything as long as you have enough terms. This is the beauty of the Fourier series. You take simple things you understand, like oscillators, sine waves, circles, and you can add them together to do something much more complex. And if you think about it, that's all of science and technology. You take these simple things and you build upon them, and you can make a complex system that can do incredible things. A simple thing can lead to something incredibly powerful.